Hi, my name is Josh Grochow. This is my video for STOC 2025 for the paper on the complexity of the isomorphism problem for tensors, groups, and polynomials 5 over commutative rings. And this is joint work with Kate Stange at the University of Colorado Boulder, Zhaori Sun, the University of Illinois Chicago, and Yoming Qiao at the University of Technology, Sydney. So this paper is all about tensors and their applications. Tensors represent higher order interactions that are multilinear. So they arise, for example, in nonlinear ordinary differential equations, cubic or higher degree, say homogeneous polynomials, multi-party quantum states, and many, many other places. And this multilinearity here means that they have a notion of change of basis, which in the case of ODEs, this is, for example, linear change of basis of the variables, same with polynomials, and with quantum states, these are the usual change of basis, local change of basis of quantum states. And so tensors are essentially multi-dimensional arrays of numbers for which a multilinear change of basis makes sense. Or rather, they're represented by these. Sometimes we refer to these arrays as hypermatrices, and the tensor is the abstract object. So for low-dimensional tensors, these are things everyone is familiar with. A one tensor is represented by a vector. A two tensor is represented by a linear map or a matrix. A three tensor is like the things I talked about before, where now the corresponding hypermatrix is a three-dimensional box of numbers. And the key thing here is that for all of these boxes of numbers, there's some notion of change of basis that makes sense. In computational complexity, tensors show up all over the place. They're related to the geometric complexity theory approach to P versus NP, matrix multiplication, graph isomorphism, post-quantum cryptography, de-randomization, classification of quantum entanglement, and many other things. And in this paper, what we do is we look at tensors over rings instead of over fields, and that lets us connect them to even more things, in particular to more groups in the setting of group isomorphism, which is a special case of graph isomorphism, to lattice isomorphism, which is another isomorphism problem that shows up in post-quantum cryptography, classification of Calabi-Yau three-manifolds from physics, and problems from number theory. So what is tensor isomorphism? I want to give you a bit of a feel for this problem before we come to our results. So you're given three tensors, t and t prime, which have indices I, j, k, because these are like three-dimensional boxes of numbers. And the question is, are there invertible matrices A, B, and C such that you can transform t prime to t by this action of A, B, and C? So the idea here is A multiplies t prime on the left, so A affects the rows of t prime. B multiplies it on the right, so it affects the columns of t prime. And C multiplies in the third direction, or it affects sort of the slices, or it's sometimes called the depths of t prime. Okay, now we can start to ask for different dimensions of tensors, what does this problem look like? So for one tensors, we said those are just vectors. So instead of A, B, and C, we now have a single matrix A. And isomorphism of one tensors is just, well, they're isomorphic if there exists an invertible matrix A that sends one to the other. So over fields, this is totally trivial. Any two non-zero vectors can be sent to each other by an invertible change of basis, and the zero vector can only be sent to the zero vector. Over rings, even this problem will become more complicated. But for the moment, to gain some intuition, let's stick with fields. So what about two tensors? So two tensors, we said, are represented by just ordinary matrices. So we now have Tij and T'Ij. And instead of A, B, and C, we have A and B. And our notion of isomorphism is just T and T prime are isomorphic if you can left multiply by A and B, some invertible matrices, to transform one to the other. So again, over fields, you may recall from linear algebra, this is completely classified by rank. Two matrices are isomorphic in this sense, or sometimes they're called equivalent when we just talk about matrices over a field, if and only if they have the same rank. So, okay, this is not totally trivial, right? Rank is an important notion, and how do you compute it and things like that, but it's still very straightforward. Okay. And then when you get to three tensors, there's a question of what happens, even over fields or higher dimensional tensors. And in particular, the focus of this paper will be what happens with three tensors over rings instead of over fields. Okay, to give you a bit more of a feel for what these things look like, I want to give you one way that we think about these objects that will come up over and over again, which is we think of a tensor, even though it is You can think of it as this 3D box of numbers. You can think of the slices of this tensor as matrices. So if you have an n by m by p tensor, you can think of that as a space of p matrices, m1 up to mp, each of which is an n by m matrix. Or in indices, you would have mk, the kth matrix. The ij entry of the kth matrix is tijk. Okay, and then we can rephrase what isomorphism of three tensors means, but now in terms of these matrices, which maybe is more familiar. And so I claim that two such tensors are isomorphic if and only if, when you build their corresponding slices, say mi and mi prime, there exist invertible matrices A and B such that the linear span of A MIB over all I is the same as the linear span of the mi prime. So here linear span means we're adding up, we're taking linear combinations of the matrices to get other matrices. Okay, and so in some sense, this linear span, that third direction where we would have had a matrix C acting in the third direction, that is accounted for in this linear span. And we'll see this in the proof. The idea is essentially that you transform this tuple, M1 up to MP. First, you left multiply them all by A, and you right multiply them all by B. And then to get things that are in the same span, you take these linear combinations according to C. Okay, and it turns out you can sort of read these equations both ways, and you get this if and only if. So for three tensors at least, when you want to think about isomorphism, you can instead think of matrix spaces, which are linear subspaces of matrices. So a set of matrices that are closed under taking linear combinations. Okay, now we come to our paper. So there are three kinds of results in this paper, and I'm going to talk about sort of the motivation and the challenges and the results for all three of them. The first is just reductions between various tensor isomorphism style problems over various commutative rings R. And this is sort of robustness of the TIR complexity class, or problems that are reducible to tensor isomorphism over a ring R. The second set of results are about group isomorphism and tensors over the integers mod prime powers. And the third is about complexity of tensor problems over the integers. And this is related to Bhargava's higher composition laws in number theory, what I mentioned before about classifying Calabi-Yau three manifolds in physics and lattice isomorphism. Okay, so first we have the first of these three, which is reductions between tensors. And to talk about this, I want to come back to what really is a tensor, right? We said it's not really just a D-way array or a D-dimensional box of numbers, right? You can't, and to get a feel for this, I want to go back to matrices. So what even really is a matrix, right? What makes a 2D array of numbers a matrix? Right? When do we call it a matrix? When does linear algebra apply to this? You can't just sort of throw any numbers you want in there and say, oh, yes, now it's linear algebra. And I argue that what makes it a matrix is how it combines with other things. So, for example, matrix vector product, matrix multiplication, and how it changes under change of basis. And actually, for a matrix, there are at least three different kinds of change of basis depending on what that matrix represents. So if that matrix represents a linear map between two vector spaces, V and W, then we can do change of basis in V and change of basis in W separately, and that corresponds to left and right multiplying this matrix L by invertible matrices A and B, which usually goes by the name of matrix equivalence. And as we said before, this is completely classified by rank. Okay. If my matrix is instead representing a linear transformation from a vector space to itself, when we do a linear change of basis on that vector space, we end up conjugating the matrix. We transform L into ALA inverse. And here, the invariants are given by the eigenvalues or the Jordan canonical form. And then finally, you can think of a matrix as a bilinear form, which is a map from pairs of vectors in V cross V to the field. And here, when I do a change of basis of the vectors, instead of ALA inverse, I get ALA transpose. And this is sometimes called isometry. And here, over any field, we have rank is an invariant. Over some fields, over algebraically closed fields, rank is a complete invariant. For example, over the real numbers, you also get signature, right? The number of ones, minus ones, and zeros on the diagonal after change of basis. And over other fields, it can get still more complicated. But these are classical notions of various notions of isomorphism of matrices, equivalence, conjugacy, and isometry. And so now we can come back to tensors and ask these same questions. What makes a d-dimensional array a tensor? I would say it's the same answer, how it combines with other things, tensor contraction, which generalizes matrix multiplication, and how it changes under change of basis. Okay, but now, instead of these maps, we now need a third vector space floating around if we have, say, a 3 tensor. So if I had a 3 tensor, that might represent a linear map from one vector space V to a product of vector spaces, W and U, or a map from V to V cross U, or a map from V cross V to U. And in all of these cases, because I now have 3 vector spaces, I need to allow 3 different change of bases. And so for change of basis in the third direction, I'll just write this as an exponent. It's not really an exponent that's meant to sort of depict in the third direction, sort of going into the page. But it's just the same action we talked about before, where C sort of multiplies the slices. It applies in the third direction. Okay. And now, when you think of tensors as matrix spaces, like I said, all of these problems turn from matrix equivalence, matrix conjugacy, matrix isometry to matrix space equivalence, matrix space conjugacy, and matrix space isometry. Okay. And now the invariants become much more complicated, and in none of these cases do we know complete invariants that fully answer the question, and even the complexity of these problems is unknown. Okay. But in the case of 3 tensors, we have more possibilities. You could also have a 3 tensor that is a map from V cross V to V, right? This is different than any of those other 3 possibilities. And so here, now you have a single change of basis matrix A in the vector space V, and this transforms the tensor by left multiplying by A, right multiplying by A transpose, just like in isometry. And in the third direction, the target, we get an A inverse. And this turns out to correspond to algebra isomorphism. So you can think of your T as a multiplication in some algebra on V. And then this action is precisely the action of algebra isomorphism. And now as invariants, you have all sorts of structures of these algebras. And then the last thing is a trilinear form from V cross V cross V to the field F. And this is just called trilinear form equivalence. We don't have a fancy name for this one. Okay. And the question is, are all of these related? Okay. Now, in previous work over fields, a lot of reductions were developed. So with Futorny and Sergeychuk, we showed that all 3 tensor equivalence problems reduce to 3 tensor isomorphism. And so 3 tensor isomorphism is sort of universal for isomorphism of multilinear algebraic structures of degree or valence or whatever you want to call this, 3. Okay. And then with Yoming Qiao in ITCS, we proved that D tensor isomorphism was actually equivalent to 3 tensor isomorphism for any D. And we got reductions in the other direction, that 3 tensor isomorphism reduces to all of these other problems. And so they were all equivalent, and we called them TI complete. Okay, so this is a diagram of a whole bunch of isomorphism problems. I'm not going to go through the whole thing, but just to highlight a few, here's graph isomorphism, group isomorphism in the Cayley table model, 3 tensor isomorphism, D tensor isomorphism, algebra isomorphism. Okay, and what we showed in previous work was that sort of all of these problems that before we had this whole mess of reductions, they were actually all equivalent to one another, and so we called that TI complete. Okay, and one of the questions in our current paper is how much of this can we extend to rings instead of fields? All right, now we come to our second set of results. And one of the motivations for these is graph isomorphism. So the group isomorphism problem reduces to the graph isomorphism problem. And so, you know, as a special case of graph isomorphism, group isomorphism are cases we're interested in solving. Okay. If you haven't seen groups before, groups are a very standard kind of algebraic structure that are used to study symmetry. And they're so standard that some people even say that group theory is the study of symmetry. And I'll give you the definition, but the intuition is just you have a set G, which in this talk will always be finite, and you have some notion of multiplication in G, which is just a function that takes in pairs of elements of G and spits out an element in G, and it should satisfy some axioms. And these axioms are motivated by things that symmetries should satisfy. So associativity, there should be an identity operation in G, and everything should have an inverse under this notion of multiplication. Okay, and the group isomorphism problem is given two groups by their multiplication tables, which are sometimes called Cayley tables. You want to decide, are they isomorphic? So here are two groups on two different sets of size 2. G is a group where the underlying set is 0, 1. H is a group where the underlying set is A, B. And these are just the multiplication tables. So these are the maps. This is the map G cross G to G. This is the map H cross H to H. And an isomorphism here is a function from G to H, which is a bijection and which sends one multiplication map to the other. So if I map 0 to A and 1 to B, you see these are really sort of secretly the same multiplication table. I just renamed the elements, right? And that really is what isomorphism is. Okay, many algorithms for this are known. In terms of worst case algorithms, when the groups are given by their multiplication tables, the first sort of not totally trivial algorithm was due to Felschen, Neubuser, and Targen independently in the 70s. That's an n to the log n time algorithm where n is the size of the group, known as the order of the group. And currently today, still the best known worst case algorithm is essentially just n to the 1/4 log n plus lower order terms due to Rosenbaum with some improvements by Legal and Rosenbaum later. There are also many practical algorithms for this problem. There was a conference a few years ago where experts on this got together and decided that even those practical algorithms, which work in much more succinct input models than the Cayley tables, they essentially don't beat this, or at least they don't beat it. Maybe they improve this constant a little bit, but it's still essentially an n to the log n algorithm. Okay, and so a major open question here is, can you get polynomial time or even just n to the little o of log n, right? Not just improving this constant here, but really little o of log n in the exponent. Okay, and coming back to the relation with graph isomorphism, in 2016, Babai showed that graph isomorphism could be solved in n to the log squared n time. And so this n to the log n time for group isomorphism really is now quite close. And group isomorphism has become a key bottleneck to further progress on graph isomorphism. And so over the last 50 years, but particularly in the last, say, 15 to 20 years, there have been a whole bunch of classes of groups sort of headed towards the general case where a lot of progress has been made. So these check marks here are all, most of them are polynomial time. A few of them are sort of getting very close to polynomial time, much closer than n to the log n. But one of the key cases where we're stuck, and that is going to be one of the things we focus on here, is at p groups. Okay, so, and this is where the relation with tensors comes in. So we said we're stuck at p groups. These are groups whose order is a power of the prime p. And so we said, from graph isomorphism, group isomorphism is a key bottleneck. Turns out that p group isomorphism is a key bottleneck for general group isomorphism. And certain cases of p group isomorphism, which are the bottleneck there, turn out to be equivalent to tensor isomorphism. Okay, so where are we stuck? These special cases I talked about are usually referred to as p groups of nilpotency class 2. So again, this is the order of the group. The number of elements is a power of the prime p. Nilpotency class 2 means that if I take the center of the group, which is the set of things in the group that commute with everything in the group, and I mod out by the center, that quotient group is then commutative. So the whole group is not commutative, but when I take this commutative subgroup, which is the center, and I mod out by it, I get a commutative group. Okay, these are, for various reasons, widely believed to be some of the hardest cases of group isomorphism, even though there's no reduction known from the general case, right? There are still sort of vague ideas of how one might get from the general case down to this case. And actually, in the companion paper to this one, in this year's stock, we give a reduction from small nilpotency class less than p, to nilpotency class 2, but it's still very far from a reduction from the general case. Okay, but recently, just a couple years ago, Zhao Sun had a breakthrough on this. So he got an algorithm for isomorphism testing of p groups of class 2 and what's called exponent p, which means g to the p is 1 for every group element, in time n to the log to the 5/6 n. So this is really, the first n to the little o log n algorithm for this problem. And then after that, there was some further progress. So there was a follow-up paper in last year's Fox by Ivanos Mendoza, Qiao, Sun, and Zhang that improved this exponent to n to the root log n. And they also extended from just exponent p in class 2 to what's called Fertini class 2. So this allows some groups where they are exponent p squared, but it still has this property that there's a subgroup of exponent p where when you mod out by it, what's left has exponent p. Okay. And then again, in the companion paper to this one, the tensor isomorphism 4 paper in this year's stock, we give reductions that extend these above runtimes to essentially all other known TI complete problems over odd finite fields. I should have said here, actually, for all of these, P is odd. And I'll come back to that at the end about the difficulty there. This star here is because we actually don't know how to do this for the reduction from DTI to 3TI. But for all the other problems in that big diagram, we know how to do this. Okay, and so where do we get tensor isomorphism over rings? Well, Sun's algorithm, it turns out, for p groups of class 2 and exponent p, goes through Bayes' correspondence, which gives you a reduction to tensor isomorphism over the integers mod p. Okay, and then essentially all the core work of the algorithm is over here in the world of tensors. But these are tensors over fields. When we drop the condition of exponent p, this same reduction with a little more work, we have to use the tensors to encode a little bit of additional structure about the group. Now, if we drop that assumption of exponent p on the group, we now have to deal with tensors over the integers mod p to the k, instead the integers mod p. So this is no longer a field. This is now a more general ring. All right. So what are the challenges in extending some of the known results, even the very recent ones, from fields to rings? The first challenge is that a lot of the known results use matrix rank, right? When you think of tensors in terms of these matrix slices, you can slice it in 3 different directions, and you can talk about the ranks of the slices, and you can use that to argue about gadgets. You can use that to partition things. There are many ways in which matrix rank gets used in these previous results. And over fields, matrix rank has, I don't know, 7 or 8 different characterizations that are all equivalent. But over other rings, those characterizations are no longer equivalent. So just as some examples, over the integers mod 6, if I take the diagonal matrix 4, 3, this can be factored as the column vector 2, 3 times the row vector 2, 3, or the outer product of these two. So it looks like it should sort of be rank 1, according to this kind of definition of rank. But its image and its kernel both need 2 generators, not 1. So you might say the dimension of the row space, if you want to think about it that way, the dimension of the column space are both 2, right? So here you see that our notions of rank are no longer equivalent. As another example, over the integers, if I take the diagonal matrix 1, 2, this looks like it's full rank. And indeed, this one is injective, but it's no longer surjective, right? In the second coordinate in the image, you can only get even numbers. And over other rings, even over other commutative rings, even stranger things than this can happen. Okay, so this is one of the first challenges, is a lot of results over fields use rank, and rank kind of breaks down over other rings. Okay, the next challenge is that a lot of the previous results assume some form of non-degeneracy in the tensor. For example, full row rank in all 3 directions. Now, over fields, you can often reduce to the non-degenerate case by just using reduced row echelon form. But the challenge here is that reduced row echelon form now doesn't work over most rings. And actually, over other rings, it's not even entirely clear what the analogous definition of non-degenerate should be. Okay, and then the third challenge is that you can have what are called non-free modules over other rings. So a module over a ring, it's just a word for a vector space over that ring. It's something where the ring can act on it by scalars, and you can take linear combinations. Okay, so over a field, all vector spaces are isomorphic to some power of that field, right? You can write a vector as a tuple of field elements. Now, over a general ring, you can still talk about, say, k tuples of field elements, and that still forms a module, but it's what's called a free module, and not all modules are free. So for example, if your ring is the integers mod 4, you can still look at the abelian group z mod 2z to the k. So this is like k tuples, but now of integers mod 2. not mod 4. So you can take linear combinations of those, but you can also use Z mod 4 as scalars on this ring, just where multiplication by 2 as an element of Z mod 4 is the same as multiplication by 0. Right? So this is what's called a non-free module. Right? Notice that this property, multiplication by some non-zero scalar, is the same as multiplication by 0. That doesn't happen over fields. Right? And so there's an additional challenge here of how do we handle non-free modules when we're dealing with other rings. All right, and now we come to how do we overcome these challenges and what results do we get? So for rank, we use one of the classical notions of rank, which is called inner rank, and it's this classification. So a matrix M has inner rank R if R is the minimum, such that you can factor M as the product of two matrices A and B, where A is an N by R matrix and B is an R by M matrix. So over a field, this agrees with our usual notions of rank. Over other rings, as I said, the various different notions of rank can be different, and this is the one that we choose to work with that seems to work out for a lot of our results. Now, even with this notion of rank, some of our results, we still need to assume something additional about the ring. And one of the things we frequently assume is that it's what we call diagonal full, which is if I have a diagonal matrix over the ring with non-zero diagonal entries, all the diagonal entries are non-zero, we want that to have full inner rank, meaning as large as possible, the size of the matrix. Now, these diagonal full rings, conveniently, they include all domains, so rings that have no zero divisors, which includes the integers, and all finite local principal ideal rings, which includes the integers mod p to the k, right? And these are going to be two cases of particular interest for us. But diagonal full rings are in general, much more general than this. Okay, for non-degeneracy, we actually have two different solutions to this in two different situations. So for group isomorphism, where we're dealing with tensors over the integers mod p to the k, we actually can reduce to the non-degenerate case, but we have to use Smith normal form instead of reduced row echelon form. Okay, and in this case, we also then, because Smith normal form, even if you started with free modules, Smith normal form can produce non-free modules, and you might not have started with free modules in the first place. We also reduce over Z mod p to the k from non-free modules to free modules. Okay. Over more general rings, in the case of tensors over free modules, where now we're assuming free module, we actually introduce new gadgets that let us avoid non-degeneracy entirely for some of the reductions. Okay, so what do we get? Our first set of results is 3ti completeness. So over certain rings R, we show that, remember, this was sort of all 5 natural tensor problems, and we look at other ones that arise in that big diagram as well. We show that these are all equivalent. They're all 3ti over R complete. And this is for free modules over diagonal full rings R, or arbitrary modules over finite local principal ideal rings. Okay. As a corollary of this, one of the core difficulties in the classification of Calabi-Yau 3 manifolds turns out to be essentially a tensor isomorphism problem over the integers. And we show that problem is 3ti complete over the integers. Now, there's a wrinkle in this in that we actually don't know. It's an open mathematical question of which 3 tensors can even arise as the 3 tensors over the integers corresponding to a Calabi-Yau threefold. But in the absence of that, if you just sort of suppose, well, maybe anything can arise, the corresponding classification problem we show is 3ti complete over the integers. Okay. And then the second thing is that there were a number of isomorphism problems over the integers and sort of more general arithmetic rings considered by Grunwald-Segal in the Annals of Math in the 80s in a series of, I think, 3 papers. And we showed that all of those problems are also 3ti complete over the integers. Okay. Now, our next set of results are sort of more in the realm of number theory. So Grunwald and Segal that I just mentioned showed that all of those 3ti problems over the integers are in fact computable just by finite means, by a Turing machine that always halts. They didn't analyze the complexity, which I'll come back to. So we were wondering, well, what happens even in small cases, say with 2 by 2 by 2 tensors over the integers? And one of our results is to show that actually this is equivalent to the principal ideal problem in real quadratic rings. So this is a classic problem in number theory. The key ideas in this reduction come from Bhargava's work in the Annals of Math. Um, and in terms of the complexity of this problem, it's actually an open question. Hallgren showed that this problem is in BQP, the principal ideal problem in real quadratic rings. And it's a well-known open question in computational number theory whether this problem is in P. So already over the integers in the 2 by 2 by 2 case, we see a very non-trivial number theoretic problem arising. Okay, and our third set of results is about group isomorphism. So Sun's breakthrough um, already sort of implies a p to the k times n plus m to the 1.8 time algorithm. And that 1.8 is improving over sort of the trivial 2 would be there, which corresponds to like a 2 to the log squared n. For isomorphism testing of two n by n by m symmetric tensors over the integers mod p to the k. Okay. What we want is instead something that's in time mu to the little o of 1, where mu is the number of distinct matrices generated by these slices. Okay. And one of the tricky things now is that different slices, because it need not be a free module, different slices can have different additive orders. So one slice might have additive order p. It sort of lives over z mod p. And if you multiply that slice by p, you get 0. And another slice might live over some z mod p to the k, where when you multiply it by p, you don't get 0, but when you multiply it by p to the k, you get 0. Okay. And so if you take mu to be just the total number of distinct matrices you can get as linear combinations of these, we want mu to the little o of 1 time. And what we need here really is instead of this k times n plus m to the 1.8, we want something that's sort of little o of, we'd rather have like k plus m plus n. Okay, and so our solution actually, I mean, it builds on Sun's technique, of which there's sort of a lot goes into it. But in addition to that, we also have to use different strategies for slices of large order, like p to the k, versus small order, like p. Okay, and the result we get in the end is an n to the log n to the 8/9 algorithm for p groups of class 2 and odd order. Okay, and so this is in comparison with the n to the log n to the 1/2 of the previous results. So this is slightly worse. And this 8/9, the fact that it's 8/9 and not a half, is because of these difficulties we had to overcome with the slices having different orders, where you can have some slices over z mod p to the k. Okay, but this is still n to the little o of log n, and it's the first n to the little o of log n algorithm in this class of groups. All right, so just to recap the results, we get 3TI completeness results and equivalence between a whole bunch of different isomorphism notions over diagonal full rings and finite local PIRs. In number theory, we showed that 2 by 2 by 2 tensor isomorphism over the integers is equivalent to a classical, well-known computational number theory question. And then in groups, we get the first n to the little o of log n time algorithm for p groups of class 2 and odd order. And finally, some open questions. So one question is, can we reduce D tensor isomorphism to 3 tensor isomorphism over more general rings? So over fields, this is known from a previous result. Our current paper doesn't cover this case. Another question is, can we extend our results on free modules over diagonal full rings to non-free modules? We can also ask, Grunwald and Segal showed that tensor isomorphism over the integers was computable, but they didn't analyze its complexity. So there's a question still of what is the complexity? And as far as we know, even just the complexity of 3 by 3 by 3 tensors over the integers is already open, right? We showed that for 2 by 2 by 2 tensors, it's open, but it's equivalent to a well-known computational number theory problem. For 3 by 3 by 3, we just don't know. Some of our gadgets, remember I mentioned those gadgets that reduce the need for non-degeneracy? Some of those gadgets turn out to be quadratic size, and so actually we can't use those gadgets in the setting of group isomorphism because quadratic dimension of the tensors corresponds to n to the log n size of the group, so you sort of negate any gains you get. And there's a question of, can we get those gadgets that let us avoid non-degeneracy assumptions in linear size instead of quadratic size. And so over fields, this is actually what the companion paper in this year's stock is doing, but still over fields. And even from that, already we get a bunch of applications, but there's a question of, can we do the same thing over rings? And then lastly, I want to highlight this thing about odd p groups versus even p groups, which would be two groups. So there's a question of, can you get isomorphism of two groups of class 2 in n to the little o of log n time? And here, many of the ingredients that go into the results for p groups for p odd either aren't known or seem to totally break down. All right, and I will leave it there. Thank you.